Hello, PCS students. We'll take a moment here to do a little tutorial on how to use Google Sheets or effectively any spreadsheet for a curve fitting operation. So what we're showing here is some X and Y data, so well, time and amplitude, which we've plotted in the chart that you can see on the screen. And you can see that there's a little bit of noise in this data. So you can consider this like a data set that you may have taken for some sort of oscillation, whether that's maybe a spring mass system or a pendulum or sound waves or any number of more or less sinusoidal type um, oscillatory motion. Um, Given that we have that data, we've got time on the x-axis, we have amplitude on the y-axis. What we are going to try to do is fit a curve to this data so that we can determine what the frequency is. We can try to approximate the amplitude, the distance from the peaks to the equilibrium middle point of the wave. We can adjust the phase of the fit to move it left and right in order to better overlap it with our measured data. And we can actually adjust the equilibrium position, the midpoint of our fit line, to see if we can bring that into alignment with the measured data. So essentially our wave form that we're going to use is as shown here in the C column. So we've got A times the sine of 2 pi times B times T, where T is the time value that we would have in our A column, plus a C term. Now, we've covered here, the A term would be amplitude. The B term would reflect the frequency of our wave. So 2 pi times frequency is angular frequency. The C term would be a phase term that shifts the wave left and right, depending on its value. And the D term here would be the equilibrium midpoint of our oscillation. So by adjusting that, we could move our wave up and down. A convenient way to enter this into a spreadsheet is as shown here. So if you look at the formula in our row, we've actually put in a series of parameters, our A, B, C, and D parameters, in separate cells. And the values of those parameters would be in cells F2 through F4. Now in our formula, you can see that we put in $F, $2. That will lock the value to the cell F2 by putting in those dollar signs with the F and the 2. If we go a little further, we've actually entered this as a cosine wave, but it's basically equivalent to a sine form, so not a problem. In our cosine term, we have 2 times the pi function times F3. So this is our B term. And again, we've used dollar signs to lock it to this cell F3. And if we click on this, it will simply highlight. Now our next term is our time value in a typical sine or cosine wave. And so here we've entered A2, which is this cell in the first column. And we haven't included dollar signs here because we don't want to lock the value to that particular cell. That is to say, when we fill down in our C column, we would like the time value to change to take on the value from the A column for every row that we represent here. Carrying on, we put in our C value from the F4 cell. If we click, it highlights it a little bit here for us. And then, of course, we add our D term, which is the F5 cell. So having entered that information, we've just put in 0 values as a starting point here. We can enter our value and it equates to 0 since we're multiplying by an amplitude of 0. If we change this to a 1 in the A value, the fit parameter A's value is 1, we see that we immediately see a new value over here that calculates based on our formula. The next thing that we would like to do is fill all of our time rows here. And there's a little feature in the Google Sheets. There's an equivalent in Excel or whichever spreadsheet you're likely to be using. If you double click on this little box in the bottom right corner, the little blue square, that will automatically fill our C column for every row on the time values. Now, they're all equating to 1 here, and that has to do with the fact that we have a 0 in our or rather zeros in our sine parameter. So I'm going to just make some changes here. I will change this to 2 initially, our frequency term, and I will change our C term. Actually, we'll leave C and D alone right now. So we can see that our values have changed, and they do seem to oscillate between 1 and -1 and back to 1. Now, it's not showing on our graph. What we can do is simply add that value to our chart by going to Edit Chart. And this will bring up our chart setup, and we can just add a new series to the chart by clicking Add Series. And if you don't see that your C column, your fit column is available, you can click on this little box, and that would allow you to simply click on the C row and click OK. And now our data shows up. Our first approximation of this sine wave shows as our red line overlapping our blue measured data here. So obviously our frequency is a little too high, and our phase of our wave is a little out of sequence. However, our D parameter does look good. If we change D here to say 0.5, we would see that our whole fit waveform shifts up. And that obviously is not as good a fit as we had when D was 0. Our amplitude term, we'll leave that for now until we get B to find the right fit. So I'm just going to just try changing our B term, our frequency term, to smaller values until we find that we get approximately the right kind of frequency. And it looks like we've more or less matched frequency here. Again, we're not perfectly overlapping, but we've got roughly the same number of cycles in our red fit line as we do in our blue measured data line. This is good. This would allow us to now shift our waveform left and right, our fit left and right. And you can do that using the C phase term in our sine wave here, our cosine wave. So we'll just try a few values to see if this can be made to shift left or right. So this would be a value in radians. We'll just put in a 1 initially to see what happens. And that's looking closer, but we're still not seeing perfect overlap between the peaks and valleys in our fit versus our measured data. So maybe we keep going a little bit, 0.2, and that's getting a little closer to overlapping. 1.3, not quite there. We can keep going. 1.4, we're getting quite close here. This is looking good. 1.5, and you can see that we've actually got very good overlap at our y equals 0 position here. So it looks like we've shifted our phase quite nicely. And at this point, really our waves are nicely matching. The only thing that's out is our amplitude term. So we realize that, okay, our amplitude seems to be from about -0.6 on the low side, 0.6 or maybe 0.65, 67, or 0.7 on the high side. So let's try a value of, let's estimate 0.65. And okay, we've got a pretty good approximation of our measured data here. This looks like we've done a nice job with our fit. And we would then, if we didn't know our frequency before, we would know that, okay, our frequency was approximately 1 hertz, which corresponds to the B term in our sine wave. And our phase term would be 1.5 radians. Our offset, our D value, is obviously 0 because our waveform seems to be centered about the y equals 0 point on our y-axis. And we did dial in a pretty good approximation of the amplitude at 0.65. We might be slightly too small on that, but it's reasonably close for most purposes. So there you have it, a very quick way to do a fit using a spreadsheet to your measured data for, in this case, a sine wave. And you could, of course, do this for other types of waves or trigonometric functions, or various data sets that you might come across in your experimental measurements. All right, I hope this has been helpful. Good luck with your data fitting.